Pretty quickly going on to the other one, which was the backward chaining. Now, when you talk about the backward chaining is the one in which what really happens around is that in general you have got what is a and or graph, and all that the backward chaining does is using a depth first search, it solves in the backward and or it solves the and or graph. So let me make it a simpler one. So there's a and or graph which is like this. These are the ands, these are the alls, and these are the ands, and these are the alls. And that's throughout. I won't be repeating things up again. Now, previously the answer was just true or false, which basically meant true or cannot say. So answer was simple. First order logic, unfortunately, the answer is not only true or false. The answer is the substitution list. So the question is not honest x comma ai, and the answer is x is equal to r2. As one substitution, there could be many, and that makes this backward search interesting. So now how do I modify backward search to work for substitution? The problem is that I could return a substitution theta over here and the same theta over here hence, but then when I apply at this branch, but then when I apply the theta at this branch in that first search, it fails. However, there was another theta 2 possible over here, theta 2 possible over here, which when applied over here does not fail. So one of the natural consequences that you could say is that in the backward chaining, because there are multiple thetas, like x is equal to r2 could be a solution here, x is equal to r5 could be a solution here, x is equal to r10 could be a solution here, x is equal to r15 could be a solution here. So one solution could be I try to find out all substitutions possible and return that and do this calculations. Wonderful. The other could be you take it like the biological neural network that which you are studying in the other course, all neurons working in parallel. They get their input and they immediately return the output. So this unit gives a theta, but it keeps computing. When it gets another theta 2, it gives it, it keeps computing. All the and all nodes are working in parallel. This gives a theta 1, and this basically is all. So this one returns all the thetas returned by here and all the thetas returned by here. This one, it takes a theta over here and checks if it's consistent with this. If it's consistent with this, checks if it's consistent with this. If it's consistent with all of them, it returns a theta over here. That's the one which is given in book, so I'll be not solving it up, of course, because the example is same as previous one. Most of things were ground. You'll get the solution at no time. Let me directly come to the algorithm as a pseudocode. So I say backward chaining of my knowledge base, and I need to satisfy in what is alpha, and this one will be more or less called as a generator. So a generator which will keep on generating things. Now there are clearly two nodes, they are AND nodes and they are all nodes, and my goal which is sitting up at the top is definitely a OR. So all I do is I call a backward chaining OR node, and I haven't made any substitutions yet. So now it's the same minimax algorithm, and I'll write the same minimax algorithm again. So backward chaining OR these are the substitutions which are made in the current branch. These are all the substitutions that are made in the current branch. So all that I do is there are multiple rules, and if any one of these rules happens to be such that my result is a feasible substitution theta, I'll just return that up. I won't wait for anything else. I will just return that up. So it's for all rules P1 and P2 and Pn. I really don't need a rule. Okay, such that I have my Q satisfied. Okay, if any one of them will need to satisfy, now is when I'll call a and on each one of on them. So I check if I get a substitution correct. So now I call a backward chaining and. What do I need to really satisfy? I really need to satisfy in the LHS part of it, which is P1 and P2 and all the way up to Pn, and it is under this constraint that, I mean, I've already satisfied my goal. If my goal would have been a failure, this would have failed. So under this substitution which has already been made, and the moment I do that up, in general you would write down a return whatever you got as a result of it, theta dash. However, I'll not use the word return because it will continue happening in parallel. Return just returns and forgets about it. I say keep on searching for rest as well. Yield. So it's a yield. And that's all. So that's my all node. The moment from any rule it gets anything, it just yields it up. It just returns it up. And very quickly I'll do in backward chaining of and. And in my backward chaining of and, all that I need to do is that I have some P1 and P2 and all the way up to Pn. I'll break this up into two parts, a first and a rest. And I'll solve it up. However, it needs to be solved on both of them, and I'll recurse over this thing. So that's exactly the same pseudocode that I need to find out what is the sum of all the elements of a linked list. You break it up into first and rest, and this one will be P1 and all of them will be P2, P3, P4, P5. This one will again be broken as first, P2 and all the rest. So let's say F as the first and R as the rest, or let me directly do it. So for all theta dash which for all theta dash such that this is satisfied. So let me get my solution from the all node. So the first of the alpha and this thing. That's substitution that I've already made. So I get this now. If it was all, I would have just returned that up. Out of all, one has satisfied. However, I need to go and solve the rest of them as well. So that's for theta double dash in so this one will be a and, so it's a recursive call to exactly the same thing. And so everything apart from the first. And And if something satisfies this doesn't fail, something satisfies this doesn't fail, then of course I yield it up. And of course I'll need a base condition. So if I get a length of alpha is equal to 0, hooray, everything is satisfied. So just yield whatever you got. And of course, if by any chance you get a error, I should write it on the top, in fact. Then I return a error. So I'll maybe just read out this code one more time. So let's go into all of them. So of course my goal node is just an all node, and that's exactly what I do. I have made no substitution. It just is alpha satisfied in my knowledge base from empty. And in order to prove that, what I do is, so I go onto all nodes. The all nodes for every rule, what I need is, okay, it's basically for all rules and substitutions. They are two rules, and I also see that renaming is not done. So let me make those both the corrections around over here. So one is there are multiple rules, and for every rule there are multiple substitutions which are possible. So there are actually two loops instead of one. So let me very quickly write this thing down. So for all rules and substitutions. So for all substitutions and for all rules, I make the in backward chaining, in forward chaining, you make the premise true. In backward chaining, you make the goal true. So for all substitutions that make the goal true, and for all such rules, all that I do is that I call in the AND function. It's equal. If any one of them satisfies, so the goal is what I satisfied over here. If I can also satisfy the premise in a recursive manner, in a recursive paradigm, under this new substitution which I have done, so if I can satisfy my premise as well, the consequent is satisfied, the premise is satisfied, I've got in my goal. Now remember, the premise is not satisfied like the backward chaining that look into the knowledge base. It's done recursively. So each one of these is now a sub goal, and each one of them will have to be now satisfied in a different recursive loop, and that's why you got the AND. Now in AND, that's exactly what I'll do. I'll go on each one of them and I'll satisfy them. So in order to do that, I broke it up into a first and a rest. The first was a call to this one, which was a OR. If some substitution satisfies this thing, I check if the same substitution around over here, whatever substitution you get, that is what will go around over here. So if the same substitution that satisfied this, which satisfies the first, theta had already been satisfied, so I applied the substitution theta, of course, first. So for all the all theta, or for all substitution which satisfy this, if it also satisfies this, then I get my solution, and it's a yield because all and nodes are working out in parallel. All nodes are working out in parallel, and if you, because I'm dealing with rules over here, then I'll also have to say for all standardized rules. So just rename if the variable names are recurring. So just rename if the variable names are recurring. So if you already use the X and there is another X, just rename that up. Now that brings us to something which is more interesting. So we looked at forward chaining. We also looked at the backward chaining where we were doing all these wonderful little things. The last one is what is, of course, the resolution. So the resolution previously was something like L1, L2, L3, all the way up to Ln, M1, M2, all the way up to Mk was given, and all that I was doing was to delete Li and Mj. And my condition was Li and Mj are opposites. Of course, in first order logic, the same thing can be unify Li, comma, not of Mj. When I say add not alpha to the knowledge base, you check out unify at every point of time, and thereafter if you get a null, you say that okay, that's not valid. And because not alpha is not valid, which means that your alpha is the one which you are able to prove. So not alpha is not valid and alpha is valid. So what you say is that in resolution, instead of just saying Li and Mj are opposite, you check out for this condition that Li is supposedly with not of Mj. Now there we also placed in a nice little rule that I said that yes, in forward chaining and backward chaining they were assumptions of Horn clauses, but I said here there are no real assumptions. And when I said that here there are no real assumptions, now it's important because there's always a for all, and there exists. Replace there exists by something new, and for all is taken care of by unification. And there you go. That's how resolution could be lifted from a more generic clause where it is a zeroth order logic into what is a first order logic. So the bottom line mantra is just a simple lifting of the zeroth order logic into a first order logic, and the only thing that changed was whenever we had to say that yes, whenever we had to say yes, these things are equivalent, in zeroth order logic it was normal, Li and Mj are opposite. Here we use unify. That's the only change that happens. One thing which I did not change was the fact that what about best friend of best friend and those infinite combinations? There is no solution to that. So you still go in the same iterative deepening format and trying to get the values. Using heuristics, you can make in very intelligent guesses. Using heuristics, you can make in as intelligent guesses as possible. But in general, if the problem is really creepy, it could go into an infinite loop. And with this, we end today's session. Thank you.